All right, now we're into section 8 of chapter R, classification of matter. And the first step is to start with the different states of matter. Solids, liquids, gases, those are usually what students learn about throughout their life. But there are more states of matter, and it seems that every couple months or so, chemists or physicists discover a new state of matter. And your book doesn't go into all of them because they're very complicated usually, but I have included what's called a Bose-Einstein condensate, and I've included plasmas in here. So you will need to know those even though they're not in your textbook. And so I'm going to actually start with solids, and then because I'll do solids, liquids, gases, and then I'll work to the other two to kind of connect everything, because we do deal with solids, liquids, and gases in our everyday life, and they'll make more sense. For your test, you will need to know information about each of these states of matter at the macro scale and the micro scale level. So they're a little different ways of looking at the same thing in a sense. So what exactly is a solid? At the macro scale, as you can see on the right here, solids have a definite size and a definite shape. And what that means is that the size isn't changing and the shape isn't changing. If you have your cell phone or whatever, it's a solid. There's nothing changing about that. And at the micro scale, solids are made up of particles, and those particles could be atoms, it could be molecules, it could be ions. It doesn't necessarily matter, but those particles are rigidly held together by intermolecular forces, and the particles, all they can do is vibrate. They do move, in a sense, but they don't move around each other. They're held in place, but they vibrate. So then that leads us to liquids, and liquids are at the macro scale types of matter that have a definite size but an indefinite shape, and it's this indefinite shape that makes them fluid. You can pour a glass of water, you can pour a glass of milk, you can pour alcohol, but the volume of that cup of water you will have doesn't change unless you've allowed it to evaporate, but then that's changing its state of matter from a liquid to a gas. If you have water in a closed container, it can still flow around in there, but it will not evaporate, and so therefore the volume will not change over time. At the microscale, the particles are still held together by intermolecular forces, although those forces are much, much weaker than in solids. But the atoms or the particles, molecules, whatever, are allowed to move around each other in three-dimensional space, and it is that fact that allows them to be fluid. So you can see that liquids and solids compare to each other in that they both have a definite size, but they're different in that they have that solids have a definite shape and liquids have indefinite shape. What makes liquids and gases similar is that they both have an indefinite shape and thus are fluids, but what makes them different is that gases have an indefinite size. You can change the size of a gas by manipulating several different properties like pressure or temperature. And we'll talk about those in chapter 8. So they're different in that respect. Gases at the microscale have particles that are no longer interacting with each other constantly. They might interact in fleeting moments when two random particles come close to each other, but it's very rare. So they're no longer held together by intermolecular forces. They move in random straight line paths, and therefore they are still fluids. If you watched the video from before where there was the scientist and Jimmy Fallon and Lucy Liu, where he was demonstrating the topic of density. You might remember that he poured vaporous carbon dioxide from the dry ice into what looked like an empty aquarium tank, but it actually was filled with sulfur hexafluoride. However, he actually poured the gas on top of it, and you could see it floating on top of the sulfur hexafluoride. It doesn't look the same as pouring water, and that's because the particles are more affected by air currents and they move around much differently because of that, and they're not stuck together in a sense due to intermolecular forces, but it still flows. If you were to have a gas move in a vacuum from one place to another, it would behave exactly the same as a liquid would. All right, so that leads us to plasmas. Plasmas are essentially superheated gases, and you may not think you encounter them a lot, but 99.999% of all matter in the universe that we know of is in the plasma state, and that's because all stars, including our own sun, are really just plasma, big balls of plasma. And the macro scale way of recognizing this thing as a plasma is that it's giving off light. It is giving off heat. It's giving off electricity and other forms of energy. What happens is that at the microscale level, the particles of what were a gas become ionized. The particles break apart. They lose electrons or they gain electrons, and they have these positive or negative charges on them. When you do that, in order to do that, they have to have super high amounts of energy because those opposite charges want to attract each other and stick together. But when there's so much energy, it's just too much to keep them together. So they fly apart, but when they inevitably do come back together, they have to release the extra energy they have that has kept them apart. And they do so by releasing it in the form of heat or light, or in the case of lightning, as electricity and heat and light all at the same time. So they gain or lose electrons to be charged. Those separated charged species come back together and they release that extra energy. And so those are the four main types of matter that you've probably heard of, maybe less so much the plasmas, but you all know what the sun is, so it's something you're familiar with. But what about the Bose-Einstein condensate? Now you might notice I went from solid to liquid to gas to plasma, and that follows the general trend of heating up the sample. If you have a piece of ice and you heat it up, it turns into liquid water. If you take that liquid water and you continue to heat it more to higher temperatures, it will boil and form a gas. And then if you take a gas and you heat it even further, it'll form a plasma. But we can go the opposite direction. And if you take a solid and you continue to cool it down, for most of the temperature ranges for typical types of matter, it won't do much. But when you get near to absolute zero, a physical change will occur in which the atoms tend to begin to merge together in a sense. Instead of a clump of millions upon millions upon millions of atoms, you get one giant conglomerated atom. And it seems weird, and it's weird even when I say this, but they start to exhibit wave-like properties. Instead of being a solid chunk, it now forms a wave. And what it means for something to be a wave is that it is massless and delocalized. And we'll go way more into this in the upcoming chapters, chapter 2, for example. But it's no longer going to behave like a particle. If I throw a particle up, it's going to come straight back down. If I throw a baseball, you could imagine the path that a baseball takes when it's thrown, or a basketball when it's shot, because those are particles. But waves behave much differently. And that's what happens to this. As a result, on the macro scale, these Bose-Einstein Condensates exhibit properties of superconductivity, which means that electrons can flow through them without any impedance, no resistance, and they exhibit superfluidity, which means that these particles, or what were formerly particles, will move as a fluid without any friction. And that's not something that normally happens. There is always friction. So it's a little strange. This was only discovered in 1995. Albert Einstein had theorized it along with a man named Satyendra Bose, who's not related to the guy who's given us Bose headphones, but they theorized this 100 years ago, and they were right that the atoms start to exhibit quantum properties. And that is 5 of the states of matter, and there are actually more. There's at least 7, but many of them have been discovered only recently, or there's very little known about them. So I don't worry about going into that. You can see here, this would be a solid, what the particles of a solid would look like. The little lines surrounding them, like here and here, those would be indicating the atoms or the particles, the molecules, ions, whatever, that they're vibrating. This picture here is just a way of demonstrating the particles of solids, liquids, gases, and plasmas, and you can read the little descriptions below them. But if you look closely at the rightmost picture, it has positive and minus signs in there, and that indicates the charges. At the very high temperatures of stars, atoms lose their electrons. The mixture of electrons and nuclei that results is the plasma state of matter. Here are some pictures that demonstrate what a plasma looks like. Those little weird globes that you see at science centers where looks like electricity is touching the guy's hand there. Those are just plasmas in there, and they're caused from electricity. Fluorescent light bulbs work in the same way. You just add electricity, the gas particles inside those tubes heat up and give off light. The sun obviously is plasma, as are lightning bolts. And right here is just another picture kind of showing the same thing, but I like how this one shows the connectivity of solids and liquids. They're both connected in a sense through intermolecular forces, all of which disappear when you get to the gases and plasmas. There are phase changes and terms for those that you need to know for your test. So if we have a solid and it is turning into a liquid, we just call that melting. If we have a liquid that is going back into the solid state, we call that freezing. If we have a liquid that is going into the gaseous phase, that is boiling. If the gas is going back into the liquid phase, that's condensation. It is not precipitation, like weather people like you to believe. It is condensation. If you have a glass with ice water in it, on the outside of it, you will see what we do call condensation, and that is correct. The water vapor in the air hits the outside of the cup, which is going to be very, very cold, and it recondenses, or it just simply condenses back into the liquid state on that outside of it. But we can also have gases going straight to straight to solids, and we call that deposition. It is depositing on the surface of something. And we can have a solid go straight to a gas, and that is called sublimation. Dry ice sublimes. You can buy dry ice at a Kroger, for example, and you go there, you buy dry ice. It's a solid chunk of material. It does not go to the liquid state, so that's why they call it dry ice, but you will see lots and lots of vapor coming off of it, which is gaseous CO2. But you can do the reverse of that, and that's called deposition. These are some pictures that I took of my car, where the picture on the left shows condensation, and the picture on the right shows deposition. This picture here kind of just demonstrates what actually happens to a Bose-Einstein condensate. And it says at high temperature, thermal velocity V, density D to the negative third. It's like billiard balls moving around. They just hit each other and bounce off. As you get to a lower temperature, you see this thing. It says de Broglie wavelength. And there's a whole bunch of stuff there that you don't need to worry about. But at very, very low temperatures, these particles are going to behave like waves. If you cool it more and more down, those waves, so over here, start to essentially align with each other and merge together. When you get to that critical temperature, as you can see here, they now form one giant wave, giant matter wave.
Matter can be found in any of four states: solid, liquid, gas, or plasma. Solid can be changed to liquid by melting. Solids can change directly to gas in a process called sublimation. Liquid is changed to gas by boiling. Gas can condense to liquid. Solids can be formed directly from gas by crystallization. A plasma is a group of positive ions and unbound electrons. Plasmas can be produced by energizing gases to give up electrons, as in this neon sign and fluorescent tube. The sun is also a plasma. Over 99% of the matter found in the universe is in the plasma state.
All right, so we have other ways of classifying matter. We have pure substances, and we have, obviously, impure substances. A pure substance is defined as anything that has definite and repeated properties through all proportions of the material. They also must be made up of one type of atom, one type of molecule, or one type of compound. Like you could have water, H2O. That is a pure substance by itself. However, if you mix salt into it, that would not be a pure substance. But every sample of water that is pure through all proportions, every molecule of it is going to have the exact same set of properties. All right, and then we have elements and compounds. Elements are the primary constituents of matter. They cannot be broken down into simpler substances, and they basically define what everything else is going to be made up of. There's 118 known elements, and you can see all of them on the periodic table. Carbon is an element, hydrogen is an element, helium is an element, and so on. Compounds are chemicals that are made up of two or more different elements. So if I give you something like oxygen, O2, that would not be a compound. It does exist, but is it an element? What is that? There's two atoms there, and we call this the elemental form of oxygen. All right. But what about, you've got O3, which is ozone. All right. The reason oxygen is considered the elemental form of the element oxygen is that it is the simplest way that it exists. You cannot have a single oxygen atom. If you have 3 oxygen atoms, that's ozone. That one is not as simple as O2, so it is not the elemental form of it. Neither of which are compounds. Compounds have, like H2O, they've got more than 2 different elements in them. This flow diagram here kind of just shows you how you can connect all of the types of pure substances. So pure substances are made up of either elements or compounds. And we can split apart elements into atomic elements or molecular elements. And so you can see atomic elements like neon are just single atoms by themselves, whereas molecular ones, like I discussed a second ago, oxygen, have more than one atom in them, but they're the same element. Now, the compounds are pure substances, but we have molecular compounds like H2O, and we have ionic compounds, which I did not discuss before, but these here are like sodium chloride. Table salt is an ionic compound. It has a metal atom and a nonmetal atom. Molecular compounds generally have 2 nonmetal atoms, and we'll get into that in a later chapter. So if something is not a pure substance, it is called a mixture. And so mixtures are physical combinations of 2 or more pure substances. The different parts of these mixtures can be separated, but they can only be separated by physical means, which means if you're doing a chemical reaction to it, that is not separating a mixture. That would be separating a substance itself into simpler or changing it into more complicated pieces. There are 2 types of mixtures. There's heterogeneous and there's homogeneous. And a heterogeneous mixture is a mixture where the different parts of it can be easily distinguished when you look at them. For example, if you look at granite, you can see black parts and white parts. If you look at the sky, you can see clouds, you can see the sun, you can see the blue sky. If you look at a checkerboard, you can see the black spaces, the white spaces, and so on and so forth. Another example might be salads. You've got the lettuce, the tomato, the salad dressing, cheese, carrots, croutons, whatever. Those are all things that you can see and touch separately. They each have their own individual properties, and even within them they have their own different properties. So the properties of heterogeneous mixtures vary throughout. Each individual component in these heterogeneous mixtures are what we call phases. All right, and then so in homogeneous mixtures, these are 2 or more substances physically combined in which we cannot distinguish those parts from each other. Think of Kool-Aid. You have water and sugar and food coloring and probably citric acid in some of them, and so on and so forth. You can't see those different parts. If it's red Kool-Aid, all you could see is a red liquid. You know there's water in there, and you know there's dye and sugar and so on, but you cannot see them with the naked eye. Solutions are also homogeneous mixtures. A solution is just another term for a homogeneous mixture, but usually it's mostly considered if the mixture itself is entirely in the liquid state, like a solution of Kool-Aid. But steel is a homogeneous mixture that could technically be called a solution, but it's not commonly done. The solvent in a solution is the most prevalent component in that homogeneous mixture. And anything else that is in there is going to be the solute. So in like ocean water, the solvent is water. The solutes are going to be the salts and any organic material that might be in there. So this picture here is another flow diagram, and this just has kind of everything all together, all of the types of matter, pure substances and mixtures. And I like how it shows variable composition, yes or no. What does that mean? So if no, it's not variable, then that means you have a pure substance. And then out of those pure substances, are they separable into simpler substances? If no, then you have elements. If yes, you have compounds. And just like the previous slide showed, you can have different types of compounds, obviously. And then if the composition is variable, yes, you have a mixture. And out of the mixtures, is it uniform throughout? If no, then it's heterogeneous. And they use the example here of wet sand. The water and the sand together would be a mixture. But if it is uniform throughout, you have a homogeneous mixture, and they use T. And I like this picture here because it shows you that there's the molecules in the tea that make the caffeine and the flavor, the tannic acid and stuff like that. Those are in there, and so are the water. But on the whole, on the grand scale, you can't see those individual pieces. So it's homogeneous. All right, and now we have differences between physical properties, chemical properties, what will be physical changes, and chemical changes. Physical properties are qualities or conditions of substances that can be observed or measured without changing the substance's composition. For example, you can rip a piece of paper. Both halves of that ripped paper are still paper. They might be smaller than the original size, but they are still the same thing. Other examples would be hardness, color, conductivity, malleability. Hardness meaning just how hard it is, like diamond is the hardest substance. Color is obvious. Conductivity, does it conduct electricity? Malleability is the ability of a substance to be shaped, a solid substance, by the way, to be shaped like with a hammer, essentially. You can take a piece of gold and you can hammer it into a sheet. And like a gold bar, you can hammer a gold bar down, apparently, into a 2 or 3 atom thick foil, and it would take up the entire size of a football field. So that is malleability. This is partially why Olympic athletes, when they win the gold medal, they always bite it to see if it's really gold, because gold is very malleable. Other ones are not, like steel is not malleable. Other examples, magnetization, is it magnetic or not, and how strong of a magnet is it? Density, boiling point, melting point, solubility. Boiling point, melting point, those are physical properties. If you take water and you boil it, the water's going from a liquid to a gas. So it's not changing its composition, it's still H2O, but its appearance is changing. Its physical nature is changing. It's no longer a liquid, it's a gas. Same thing with melting from ice to water. Solubility is a physical property, and this would be like how much of a substance will dissolve in a certain amount of solvent, usually water. So, like salt, for example, you can take a pinch of salt and sprinkle it into a cup of water, it will dissolve completely. Or you could take an entire, store-bought container of salt and you could pour it into a cup of water. Not all of it's going to dissolve, but some of it will. How much of it actually dissolves? That is its solubility. Physical changes are changes that occur without changing the chemical composition of the substance. Like I said before, ripping a piece of paper, boiling a liquid, freezing a liquid into a solid, cutting, breaking your bones, those are physical changes. So how do chemical properties differ from physical properties? Well, chemical properties are properties that can only be identified or measured by undergoing a chemical reaction. For example, does iron rust? Yes, it can rust. However, it can only rust under the proper conditions. It has to have water present and it has to have oxygen present for that iron to rust. And so that is a property of iron, its ability to rust. What you will notice with chemical properties is that they are much more specific than our physical properties. Does ethanol burn? Yes, it burns in the presence of oxygen with enough energy to overcome an activation barrier. Those are all things that are very, very specific. Here's another example. Does hydrogen gas react with water? And the answer is no. So it's not a chemical property of water that it reacts with hydrogen and vice versa. So you have to be very clear in there about if they're going to react and then what are the conditions that they react with. Chemical changes are changes that happen to the composition of a material. So right here you can see in the picture there's some mercury down here and there's iodine right there. You have a liquid metal and you have a solid nonmetal, which happens to look like a metal, but I promise you it is not. When those two react with each other, they make a completely different type of substance. You can see over here, it forms two different products, one that is orange, one that is yellow, both of which are solids coming from a liquid and a solid, and both of which are clearly not colored. And so chemical changes you can notice by color changes, by light being emitted, like in a glow stick, heat being given off, like in a fire, or heat being absorbed, as in a cold pack, which, if you have a cold pack in a first aid kit, you literally break an inside container that has a chemical in it, and it mixes with something else that's outside of it, and that reaction that occurs between those two actually suck energy from the surroundings into them. And since you would be part of the surroundings and you're having energy sucked out of you, you feel colder. That's an endothermic reaction. So we have light being given off, we have a color change, we've got energy changes, whether it's gaining or losing energy. If gases are emitted from the reaction, like if you mix vinegar and baking soda, like in the typical volcano experiment, that gas is a product of the reaction. It's carbon dioxide. So the evolution of it is an indicator that there are chemical changes occurring. You could have a precipitation reaction where you mix two clear, colorless liquids together and a yellow solid precipitates out of that solution. And we'll get into these in chapter 6, but a solid forming from other things indicates a reaction has occurred. The last bit here in this section is about separating mixtures. And there are many ways that chemists can separate mixtures of compounds or molecules or elements. But the ones here are some of the most basic. First is a distillation. And distillation uses differences in boiling points to separate usually two liquids. So if you know anything about distillation, you probably know that a very common form of distillation is the production of purified ethanol used for drinking, like in moonshining. And so what happens is in these mixtures of water and ethanol, you have right in here water and ethanol. You're going to heat that up with a Bunsen burner, right there, that will cause the ethanol, and this is distilling water in a sense, but if it was a mixture of ethanol and water, what would happen is the ethanol, which has a boiling point of 76 degrees Celsius, the ethanol molecules will begin to boil and go into the vapor phase before the water does, because the boiling point of water is 100 degrees Celsius. Since you've got that 24-degree gap in boiling points, the water molecules will stay in the liquid state at 76 and 77 degrees and so on, but the ethanol molecules will escape. They will travel up this tube to here. The thermometer will record that temperature, and it would be 76 degrees for the if this was ethanol in there. But this is clogged up in there, so the vapor would continue in here and through this inner tube in there. Outside of that inner tube is cold water, which would go in here, and it would fill up that outer tube surrounding the inner tube, and it would end up flowing out. That cold water, usually ice cold water, will recondense the ethanol. So you'll get liquid ethanol over here, which will drop into that flask, and you get ethanol there, water over there, and now you've separated the two. One of the key things to remember for these separations of mixtures is that they're always done by physical means. And boiling point is a physical process, so it must be a physical method of separating two liquids. If the boiling points are too close together, it will not work though. All right, the next way to separate a mixture is by filtration, and this method uses differences in sizes of particles. Everybody who has a colander or a strainer at home is using a filtration, or if you use coffee, if you drink coffee, the coffee filter, hence filtration, is keeping the coffee grounds out of your drink. They're too big to go through the paper, but the solution of coffee is small enough to pass through the holes. We can separate mixtures in a technique called trituration, and trituration uses a solvent to dissolve impurities that are mixed in with a desired chemical that must be a solid, while the desired chemical remains undissolved. So you're forming a solution of things you don't want, and then you basically just get rid of them. You can just decant them out, pour them out of the flask they're in. What remains is a pure solid, and I've got a video here that shows how a trituration works. All right, and we can do what's called a liquid-liquid extraction, which is essentially the same thing as a trituration, but here the compound you want is not a solid, it's a liquid. And it uses this piece of glassware called a separatory funnel. And so basically what happens is you're going to have, generally for an organic chemist, two layers, a water layer or an aqueous layer and a organic layer, which will be up here. And so if your compound is an organic molecule, it's probably going to be like an oil, and every reaction makes impurities that you don't want. So you have to get rid of them. And if your compound is a liquid, there's going to be salts in there and maybe some water and whatever, depending on the reaction. So what you can do is add some more water to get rid of those salts. And it could be salt water to make the water even more polar than your compound, so they separate much better. And then you can do something to the compound you want to dry it out, get rid of any water that might still be in that top layer up here. But you could do that. Or if the compound you want is soluble in water and there's other things there that are not, you could simply add more of an oil type compound, like acetone, for example, and that will get rid of all the organic materials you don't want, leaving you with just water. And then down at the bottom of this separatory funnel is a stopcock. So whether you want the water layer or not, you just turn the stopcock and you open it up, and the water will drain out of the bottom of it, and you would have a flask down here to catch it. And then so if you want the oil layer, you just get rid of all of this. That would be gone, leaving you with just the oil layer. And I've got a video to show that here as well.
So this is a set funnel, and what we can use this for is to extract certain materials into an organic layer while it's in from an aqueous water layer. And so what's important about the two of these is that you have to use two solvent pairs that are miscible. And so the reason for that is that if they did mix together, you would be able to extract one material into another one. And so in this case, we're going to use water here, which I've dyed yellow so that we can see the difference clearly, because water and dichloromethane, which is the other solvent, look the same. So once you have your two solutions, you can pour each into the set funnel, and you want to make sure that this is closed so it doesn't pour right out. And when pouring your second solution in, you want to make sure you pour it gently so that it doesn't splash everywhere. So you'll see right away that they've started to form layers. And so what next we want to do is to cap this and start mixing. And when you do mix these two products, you create an amount of gas, so you want to vent this right away initially. And so you'll hear a hissing sound whenever you do vent it. And so you can shake it up a little bit, open up your end again, and you'll hear this hissing. And so we can mix this multiple times until the hissing actually stops. So when you let it rest for a little while, you can see the two layers form. And in this case, we've used dichloromethane and water. And so dichloromethane is actually heavier than water, so it'll be the bottom layer, but with a lot of different organic solvents, we'll see that layer on the top instead. And so before you start to pour, you want to make sure that your stopper is out so that it will actually come through. And then you can just open this up, and that bottom layer will pour right through. So you want to be careful that you don't get the water layer as well as the DCM layer. So once that gets pretty close, you can cut it off, since you know that what product you want is at the bottom. So we let the bottom layer run through the bottom, but when we're collecting the top layer, we want to be sure to pour it through the top of the set funnel instead. Simple as that.
All right, the last technique I have here for you for separating mixtures of compounds is chromatography, and this uses a difference in polarity. And so you can see in the picture over there on the right that basically what would have been probably ink dye or something has been separated on a piece of paper. And the way this works is that you would spot the piece of paper. Let's say that's probably black. You'd spot it right there on that line. This one probably looks like it was bluish right there. That one looks like it's yellow, and then on the right it would be red. And so you could spot those different inks, and you put that inside of a beaker, and the beaker has a tiny bit of solvent in it. And so let me show that, what that could be like. So you take a beaker. Don't mind my drawings here, because obviously it's terrible. But you put that in the beaker. The solvent is slightly below the line with the dotted pieces of ink, I guess. And eventually, through capillary action, the solvent will run up that paper. But what goes on is that the chemicals in those dyes are going to interact with the paper as it's moving up and the solvent. Since you have polarity differences going on, the different compounds being different polarities, they will move up at different speeds. And you can see in this, whoops, I thought it would go together, but it didn't. You can see, there we go, that in the ink on the far left, the yellow compound in that dye moves the fastest. And it kind of correlates to that ink right there. In dot C, in what was probably a blue dye, you can see that a compound up there is moving the fastest. And then in red, it's staying right there. And eventually, if the paper was long enough, they would completely separate, and you would just get yellow, blue, and red dyes that make up any color. So I got a video showing how all of that is going to work. So let me get that up.
You always say I'm unromantic. Don't know ways to make a girl tick. I must say you're right about this, for I am truly unpoetic. But I am not dumb. I'm not that stupid. It's just that sometimes brain not working. So I didn't sleep. Use my little wit to write this little bit. You are my ice kacang in this tropical heat. You are my favorite dessert, so inviting, so sweet. Would you like to bobo cha-cha? Come along and dance with me. For you are my love, my tutti frutti, someone I'd like to eat. Sha-la-la-la. Every time when we go dating, first the movies, then go shopping. You always hint I'm unexciting. It has been so since the beginning. But I am not love. I'm not so stupid. It's just that sometimes I'm a blockhead. So I didn't use my little wit to write this little bit. You are my ice scotcha in this tropical heat. You are my favorite dessert, so inviting, so sweet. Would you like to bubble cha 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 cha? Come along and dance with me. For you are my love, my one hot of tea, someone I'd like to eat.
Each time I look into your eyes, I see some pretty colors.
Very nice.
I wouldn't mind paying any price. I've got charm over you.
I say go honeydew. You are my ice scotcha in this tropical heat. You are my favorite dessert, so inviting, so sweet. Would you like to bubble cha 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 cha? Come along and dance with me. Oh, you are my love, my tutti frutti, someone I'd like to eat. Ice scotcha.